Good evening, good afternoon, ladies and gentlemen. My name is Kellby Solano.
John Perez.
My name is Fontus.
And this is our project on the desalination of seawater. First and foremost, we have to address the issues concerning the water supply. As most of you know, roughly 75% of the Earth consists of water, but only 2.5% of the water on Earth is fresh water. And as you can see in the figure, most of it is trapped in glaciers, and most of it is found in groundwater. And that's a growing issue with the Earth's rising temperatures and the melting of glacier ice caps and the depletion of groundwater resources. Not only is 1.2% of water available fresh water found on the surface. In order to address our global learning, we wanted to bring awareness about our global concern. As you can see in the figure, there is a global water stress all around the globe in areas such as North America, the Arabian Peninsula, and East Asia. And these areas do suffer from frequent and severe droughts, which can lead to water restrictions, economic struggles, political struggles due to that fact. These areas do have limited access to clean drinking water due to poor infrastructure and poor management found in some of these countries. And one other thing that we also have to address is that the fact that there are some desalination plants found in these areas as well. But the negative thing is that they are rather expensive by the means of which they desalinate water, and they have a negative environmental impact in the sense that the brine disposal. So here we have our problem statement. Can we modify the solar collector to desalinate water in compliance to acceptable water standards using only thermal radiation from the sun? Now we had to change our initial objective of desalinating water for human consumption because due to the health concerns I will address shortly. So now we're just limiting the desalination of water to be used at home for cleaning, sanitation, so on and so forth. Here we have our design flow for our system. We have thermal radiation from the sun going into our control volume here. Here we have a solar collector that will be encased in solar reflectors and with an acrylic top to emulate the greenhouse effect. And we'll have water circulating between a boiler and the solar collector so that it's constantly being heated up. And then we want to produce water vapor. The produced water vapor will then enter a heat exchanger, which will also have an input of cooler water and an output of fresh water. Here we have some of our conceptual designs. To the left, we have our initial conceptual design of the heat exchanger. The second picture in the middle is a section view of our heat exchanger, proposed heat exchanger. And then the third picture here is the modifications we made to the solar collector. So we have it here on a plank, so that it's able to pivot and face the sun during different times of the day. Here we have some previous desalination designs. Figure 1 shows the desalinator, which is a small scale unit, but it does use solar panels. The pure aqua ink, as seen in figure 2, is a larger scale system. It's able to produce more clean water, but it's rather costly. And then figure 3 shows a rainmaker, which was greatly influenced our initial design for the heat exchanger. These are some of the engineering standards we tried to abide by. Since we are dealing with high temperatures, ASME says that we can't exceed 186 degrees centigrade. But since we're just trying to get water to boil, we were in compliance with that standard.
So now that our system deals with the distribution of water, we want to look at some standards for quality drinking water. One of this was the Safe Drinking Water Act, which is established by EPA. Now this act is a standard that governs the amount of contaminants that can be in quality water. And it's divided into 2 separate sections, primary standards and secondary standards. Primary is for the health benefits, and secondary standards are the amount of contaminants that would cause odor, taste, and discoloration. So next thing we want to take into consideration is the distillation process. Distillation provides water that is free from contaminants and minerals. And at this state, this water is an active absorber and absorbs carbon dioxide, which makes the water more acidic. This can cause health effects, and also the lack of minerals in the water can cause health effects. So that's why in our project, we want to use the water for more purposes such as cooking, cleaning, and also for irrigation or watering plants. However, if the consumer did want to use the water, adding minerals will increase the pH level and also negate some of the health effects. Here are some of the parts we used. We need a 12-volt battery to charge our pump. The pump we selected was a high temperature pump that's able to work from 10 to 100 degrees Celsius and also has a 9 to 3 meters. Because of the way we set up the design, we needed that at least this to get our the height difference between the water and the system. And also we wanted to use thermal piping, which can operate at temperatures of 260 degrees because we're anticipating hot water. Secondly, we used a soldering kit. Because of our heat exchanger using pipes and fittings, we needed to make a system that was leak-free. Also use the Atkins thermocouple to get the measurements of temperature on the soil collector, and also copper pipes. Use type N copper because type N copper offers a wall thickness that is small, and which would make the heat transfer process between the hot and cold fluids more efficient, and also because it's resistant to corrosion and long lasting. Here are some of the ProStrack constructions. As you can see here, is our stand with the soil collector, the modifications we made to it. And you see it's angled towards the sun, offering the more area for the sun's rays to hit, which would make the heat transfer process more efficient. Also here, you can see the reflector and also the containment chamber, which kept the solar collector hot and also kept the heat close to the solar collector. And lastly is the heat exchanger, which you see on the right. Here's a cost analysis that we provided the initial cost of the solar collector, which is $363, and also the cost of modifications, which is $186. So in total, it's like around $500 for the whole system. And as you can see, the cost of modifications were $186 because we're able to get materials that were standard sizes and also materials that were readily available to us. So that decreased the cost of pending modifications. Some technical knowledge we took into consideration was the thermal properties of water. In this graph, we can see the area of the water is large, and that's how much energy is needed to power or boil water. So we need to take that consideration on the design and what we need to do. Also, the thermal conductivity was, since we're using heat transfer, we want a material that has a high thermal conductivity to transfer the heat. We took in the concept of forced convection, being able to pump the water through the solar collector to get that output hot water, and also the greenhouse effect and solar radiation through the solar reflector, being able to trap the heat inside of a chamber and also reflecting the light back into the solar collector.
All right, so experimental formulation. So first, for testing, we decided to first test the solar collector without its modification. So doing that with and without its accredited cover. And so we obtained kind of a control results, and then after that we performed the proposed modifications to the solar collector, like adding the parabolic reflectors and constructing the mechanism to be able to adjust to the sun's various angles, which was one of the disadvantages that we have with the solar collector. After that, we manufactured the heat exchanger, and then after that, we conducted the test with the modifications to the solar collector and compared the results to the control results, and doing that with the accredited solar reflector cover, and then if we were able to heat hot water hot enough, compare fresh water versus hot water. We decided to remodify our solar collector because of the issues of the daylight visibility for Miami and the fact that the sun changed many angles given the day and the season. So that was one of the disadvantages we had with our solar collector, was that it was on a flat surface, it couldn't adjust, so if the sun was at a certain angle, there were some areas of the solar collector was not getting heated. So we redesigned our solar collector by placing it on a cart that we could rotate 360 degrees depending on the sun's position, and also a pivot joint so we can adjust the angle of the solar collector to be parallel to the sun. And also, since we were working with a thermal system, we did an analytical model of a simple system of a flat plate, so we kind of see how hot would the metal get if it was just exposed to the weather and if you left it out to get heated up by the sun. And we assume conditions are similar to our solar collector, like it's insulated by plywood because our solar collector is supported by plywood. And also we made assumptions like cost of solar energy, which means that there's no clouding, that means it's just consistent sun energy being transferred to the solar collector, and a similar surface area of 0.32 to the solar collector. And as you can see here, you have the results of what happens is that you get a nice curve in our model. And it shows you that at a point you reach steady state because you're losing a lot of thermal energy with this copper to conduction, radiation, and convection. And even in the fact when you have no wind speed, you still get major losses due to conduction and radiation. But one of the issues we have with our analytical model was that since we were taking basic assumptions like there is no cloudy weather, it differs greatly from the experimental results, which are shown on the right, and this is an experimental result, analytical model results. And as you can see, when you have the weather conditions, you have some times where it's heated up at a given amount of temperature, and then it starts decreasing because clouds end up blocking out the sun, which reduces the amount of thermal energy transferred to the solar collector, and then it's not a nice cooling rate because the different wind speeds are not consistent all the time, like in an analytical model. So here we have the experimental data without the modification. So this is before we did any modification to the solar collector. On the left you have it with cloudy weather conditions, and then on the right you have it with sunny weather. So on the left you have in red the surface temperature of the copper, and on the bottom we have the outlet temperature of the water, which means the temperature of the water as it leaves the soil collector and then enters the boiler. And it reaches steady state because of the port. It keeps losing energy to the conduction and convection. And when it's cloudy weather, you don't really get high temperatures. You get a temperature around 40 to 45 because of the low amount of sun energy being transferred to the soil collector. So you're seeing results in the outlet temperature. And here you have, like when you have sunny weather, you can get the soil collector. On this given day, we got it to around 70 to 80 with max surface temperature being 80 degrees Celsius and the max water temperature being 45 degrees Celsius. But this isn't that accurate because at the time we had leaking, and that was before we fixed the leak. And here is experimental data with modifications. So this is after we modified the soil collector, and we did it so we can fix the angle towards the sun. And in the beginning, we had like a cooling because there was cloud for like a couple minutes, and then after that we had results of like an hour of just consistent sun. And we managed to get the solar collector around 60 to 65 because of the low amount of solar radiation we were getting from that day. And we managed to get the outlet temperatures of the water around 40 to 45 degrees Celsius. And there's a big, huge difference because of the fact that the solar collector has a huge amount of surface area, and most of the surface area is just the solar collector, not the piping itself. So you reduce the amount of thermal energy being transferred to the piping. So here we have a video of our experimental setup. You can see here, you're going to see this is where we keep the battery, the boiler, and then the pump is on the bottom, pumping the water to the solar collector. Right now, the solar collector is angled facing the sun, so that we can heat up all the surface area of the solar collector. And then right now, it's the solar reflector, so there's like reflectors inside of aluminum foil. And then we have plastic wrap to keep in the hot air inside. And also, we make sure, like when we're getting data from the boiler, we decided to block out the sun and stuff like that, so that we make sure that the water is only heated up by the solar collector, so we can see how much heat was being added by the solar collector. And as mentioned before, some of the problems we had with testing was that we had leaking of the solar collector in the beginning, so it's something we had to fix. But we managed to fix that when we got the right kit. And also that on many days that we wanted to test, we ended up with cloud cover, so we weren't able to gather the desired data, or we had limited amounts of data, or screw our data. And also when we designed a solar reflector, before we reinforced it, we decided to run a preliminary test, but then we didn't take consideration that it was very windy that day, and it ended up causing our solar reflectors to be damaged because the high winds would kind of reduce the concavity. So what that would do is that it would create kind of these shadow spots on our solar collector, so that there would be spots that wouldn't be heated up properly. And also, since it's a big solar reflector area, the high winds would cool it even faster than it normally would be.
Now that we've talked about the problem and shown our design, we have to put things in perspective. More than 1 billion people have limited access to clean drinking water and sanitation. And roughly 3.4 million people die each year from water-related diseases. And this number is expected to increase as the world's population increases and as climate change greatly impacts the water levels. So here are some of the recommendations for our senior design. We saw that the solar reflector was rather costly, so we want to try to manufacture smaller solar collectors with the same amount of material. Therefore, having a tighter pipe system so that more thermal energy can be absorbed. Have a number of solar collectors connected in series so that no one solar collector is being losing heat due to forced convection more than the others. In addition, we want to try to incorporate solar cells to power the pump and make the system more self-sufficient, and incorporate a boiler and heat exchanger into one unit as opposed to having them in two different components. And of course, one thing that we could recommend is set deadlines to avoid delays and improve on-time management.
So future works we would like to add to our design was test solar collector in areas with higher solar irradiation. As you can see, Florida here is in the orange area. However, there's areas where there's higher solar irradiation. If we're exposed to more radiation, more sunlight, then we'll be able to create higher temperatures of vapor and have more condensation and create more water. We would also like to improve the solar collector and heat exchanger to make it more marketable, just with materials and also the size to be able to last in different environments, and also work in collaboration with the health agencies and also health officials, because as we mentioned before, distilled water has health effects, and we'd like to have these addressed so that the water can be consumed and also used for other applications. So in conclusion, one of the main forces for our distillation process was water vapor, and we're able to create water vapor with the modifications that we provided. However, it wasn't to the results that we desired or the optimal results. And this was just due to the dependency of the solar collector on the clouds and the weather. If there's too many clouds, then the data would be inconsistent or not constant. So also we would like to research why there is water stresses located in areas displayed. Usually in areas of like water stresses, there's a lot of solar radiation. So those areas would be the places we'd like to have our design and our solar collector there, which would also just solve the water crisis, but have a lot of sun to help the process. And those are the downsides, but however, we're able to get the temperature to rise significantly under the greenhouse effect by having that chamber and also reflecting the light back onto the solar collector. And we just recommend, once again, because of the distilled water, that it be used for cleaning and also agriculture instead of consumption. So here is our project timeline and also the division of responsibilities. And thank you. We'll take any questions.
Thank you.
Why is your solar collector shaped that shape instead of flat? So
Yeah. So we decided to do that because we wanted our solar collector to be parabolic, and with the parabolic we get the reflection, so we kind of increase the height so we get to hit most of the spots of the solar collector, and we kind of enclose it on top.
the reflection from where?
Towards the different heights of the solar collector and the different spots of the parabolic shape.
Parabolic reflect light to a single point,
Yeah.
a focal point, which is outside of the.
Yeah, so yeah, it does it to a focal point, but if you're not at that focal point, it passes on. But then since our solar collector is tall, it's able to hit even though it doesn't hit the exact focal point.
Go back to the video. You should play over tonight. Now the part there facing us right there,
Yeah.
that's your collector there, wrapped in plastic wrap.
Yeah.
And that's salt water you put in there, correct?
That's regular water.
Regular water?
Yeah.
So where's the salt water going into?
The salt water, right here, there's a boiler. So then we put all the water inside the boiler, tested it at ambient temperature at the 25 degrees. And then what would happen is like it would go, you see those two pipes? It would go down the pipes into the pump and into the soil collector. And we didn't have the chance, like during testing, we wanted to use just regular water because seawater has different things in it that like we wouldn't be able to control and might break our system before we even got to the testing. So this is like one of the preliminary tests we used with regular water. And because like the closeness of the water to seawater, just like with adding different materials in like the salt and whatever, and things like that, it would raise the temperature a little bit, but they have close similarities to just regular water. So yeah, the water would go through the system and be heated up, and then at that point, we see the thermometer right here, going to the inlet, the outlet water, which we'd have here, and we'd collect how the temperature was at.
Say you put in the spectral ratios, say you put in a gallon of salt water.
Yeah.
You do the process, how much fresh water are you getting out of that gallon?
Out of that gallon. Right now, we had 1 liter, and we're able to get like all the water back due to like stoppage of leakage. Once again, we're saying how we were able to get condensation in this chamber. However, as you can see, we only got it up to 45 degrees due to like the time of day we went out there, and also if we're other places like where there's more solar radiation, we get more. However, at the 40 degrees, there wouldn't be a lot of condensation, but like however, once we go to like other places where there's more radiation, then we get like higher temperatures at like 60 or 80 degrees. And even at 40 degrees, there's condensation, but not a lot. But like at 60, 70, 80, 90 degrees, you get more condensation and more water at the end.
Okay, when you're saying 40 degrees, you're talking Fahrenheit or Celsius?
Celsius.
Celsius.
Yeah. Not for
Formulation,
you got 40 degrees Celsius.
Yeah, I was trying to see how it was working, because the video went so quick. I was
No,
trying to picture
yeah.
it.
No, yeah, it just goes down through the pump, through the solar collector, and then up into the same container. So it's like, yeah, it's like, it's a closed system, so like all the water is being, all the water goes back into the solar collector. Yeah.
To make this a global solution for water source, what would you have to do?
To make it a global solution for water sources. As in how we market it or how we bring it to the consumer?
Not the marketing, what would you have to do differently on your system
Mhm.
to be able to provide it to third world nation
Definitely.
for, let's say Africa, provide it to Africa for,
Definitely. Yeah, like, so
for
what
an
we're,
application?
yeah, what we're trying to do in our system was using, like, as we're saying in the cost analysis, our materials was like around $186. So we wanted to like choose materials that were readily available in different countries, like nothing that was too custom, nothing that had to be made outside the country. So the materials we use here, like copper pipes and also like the different tubings are like ready available. We found them at the nearest Home Depot and things like that. So we think that these materials would be ready available to those countries. So just making those materials, like using materials that are cheap and like available and not custom, we think that having that and like just being able to build it at that country would help like.
So how would you manage the mineral?
The mineral water, yeah.
The demineralization?
Definitely. We saw it in the slide that like we were talking about distilled water and how like there's no contaminants and also no minerals. So there will definitely be health effects if there's normal consumption of the water. So like that's why we're recommending it for other uses and not for consumption. However, there are like we leave it
Well,
up.
that won't help the global solution.
Yeah.
So you need to figure out what you would do in order to
For sure.
make it drinkable.
Definitely.